An easier way to add vectors is to use the mathematical method. To do this, we need to get the components of each vector. Since the vector is the hypotenuse or the long side of a right triangle, we can find the x and y components by multiplying the size of that long side by the sine and cosine of the angle the vector makes with an axis. The way we do things, we use the positive x-axis as our origin and we go counterclockwise. If we do it that way, then the x component is always cosine and the y component is always sine. For example, if we have a vector that's 3.6 units long and it's 33.7 degrees above the x-axis, that gives us an x component of 3, and then a y component, 3.6 times sine of 33.7 of 2. We do the same thing with our blue vector. So we've got our red vector, blue vector, find our green vector. We do the same thing with the blue vector. Here we have a couple of choices. We could define our angle counterclockwise from the negative x-axis. We could call it clockwise from the negative y-axis if we want. But if we want to do it clockwise from the positive x-axis, that would bring us all the way around more than 180 degrees. So it's got to be 180 plus 11.3. Now, if we don't do that, if we just say, well, it's 11.3 degrees below the x-axis, in that case, our x would still be cosine, our y would still be sine, but you notice we got positive numbers for both of those. We have to put in the minus sign. Since they're both, it's to the left and down, it's going to be minus x and minus y for our point here. We have to put those negative signs in by hand. If instead of 11.3 we do 180 plus that, or 191.3, then we'll automatically get negative 5 and negative 1. You can see that if we do it this way. This is the reason I do it. It's kind of easiest to do it this way and not have to worry about where do we have to add or subtract a minus sign. I don't have to worry about it if I'm doing it like this, because I can just be mindless and say, well, it's always, whatever I get from the calculator. You do whatever you want when you're doing problems, but you should make sure that your convention is obvious to everyone. So if we want to add vectors mathematically, what we have to do, get the x and y components, add the x's together, add the y's together, and then put the total x and total y into the Pythagorean theorem like this. We find the arctangent from total x and total y with this ratio. One thing we have to watch for, though, let's say we have our total x is 3 units and our total y is 7 units. We would do arctangent of 7 over 3, and we get 66.8 degrees. That's fine. However, if our total x had been negative 3 and total y had been negative 7, the arctangent would still be arctangent of 7 over 3, and we'd still get 66.8 even though we're pointing in the opposite direction. So in some cases, we'll have to add 180 degrees to our angle to get the right answer. The reason for this is tangent is periodic over 180 degrees instead of 360 degrees. This is something you have to watch out for when you're adding vectors. You look at the components of the resultant and make sure you're in the right quadrant, or see if you have to add or subtract 180 degrees. What if we want to add 3 vectors? These can be velocities, that's fine. We can say you're on the deck of an aircraft carrier, it's moving 15 meters per second due east. You're walking across the deck to the north at 5 meters per second. And while you walk, you throw a rock 27 meters per second in a direction 31 degrees south of west. What would someone in the ocean see for the rock's speed? So first we have to get our components. If east is our plus x direction, then the aircraft carrier's velocity components are ax is 15 cosine 0, and y is ay 15 sine 0. So we get 15 meters per second in the x direction and nothing in the y. Your walk, if you're walking to the north, that's 90 degrees. Bx is going to be 0, 5 cosine 90, but by is 5 sine 90, or 5. Finally, if the rock is going 31 degrees south of west, if we measure from the plus x-axis, which is east, around counterclockwise, we get 211 degrees. Our component cx then is 27 times cosine 211, or negative 23 something. And our cy is 27 sine 211, negative 13.9 meters per second. Then we add them all up, ax, bx, cx. We get negative 8.14 meters per second. Add the y's up, we get negative 8.91 meters per second. We find the magnitude by squaring each of those, adding them, taking the square root, we get about 12.1 meters per second. Direction, we get the arctangent of y over x, so negative 8.9 over negative 8.1. Your calculator will give you 47.56 degrees. That's what this math program, Mathematica, is doing here, only it works in radians, so if I want degrees, I have to multiply by 180 over pi. The problem here is 47.56 is northeast. Since total x and total y are both negative, we should really be southwest. We have to add 180, and we get that the real answer is 227.56 degrees. Now we do the same thing. Any 2 vectors, 3 vectors, 500 vectors, however many we have, we do the same thing. Get the components, add the x's, add the y's, combine them using the Pythagorean theorem and the arctangent. If we need to subtract vectors, a minus b is the same thing as a plus negative b. So in other words, get the components of b and multiply them each by minus 1, and then just add it to a. Now, we can also multiply vectors instead of just adding them. There's 2 different ways we can multiply them. We've got the dot product, which is also called the scalar product, and the cross product, which we'll get to next. The scalar product, of course, gives us a scalar at the end. If D is our scalar product of A and B, we can write this as AX times BX plus AY times BY. We put in these numbers and we notice we get 0 here. The reason is our aircraft carrier, which is A, was moving to the east, and U, B, were walking to the north. There's a 90-degree angle between those 2 vectors, so they have no component in common. Walking to the north doesn't get you anywhere in the east-west direction, either way. And the same way, if you're walking in the east, you don't make any north-south progress. So whenever 2 vectors are perpendicular, we'll get 0 for the dot product. So this is one way to do it with components. If this was in 3D, we'd also have plus AZ, BZ. The other way we can do this is you get the dot product by taking the magnitudes of the 2 vectors and multiplying by the cosine of the angle between them. So we can do F is C dot B. We know the magnitude of C because we found CX and CY. We find the magnitude of C, which is CX squared plus CY squared. Add them together, take the square root, and get 27. The magnitude of B is BX squared plus BY squared. Take the square root after we add them and get 5. If C is pointing to 211 degrees and B is pointing to 90 degrees, then theta is 121 degrees. So you have 27 times 5 times the cosine of 121, we get negative 69.53. If we do the component method, we get negative 69.53. They have to equal. You'll probably have a homework problem where you get components of 2 vectors and you're asked for the angle between them using this method where you have 2 different ways to do it and you can set those 2 ways equal. That's a good way to solve that problem. When we look at work, this will be useful. This is going to be defined as the dot product of force and displacement. If we have 3 people pushing on a train car to move it, what we notice, these 3 vectors all have the same length, so they're the same force. The red vector is going to do the best job of moving the train down the track. The green vector is less effective since part of that force is dedicated to trying to tip the train car over. And the blue vector will do absolutely nothing to help because it's all directed in tipping the car over. None of it is in the direction of motion. So again, the reason is the blue and the red vectors are perpendicular, so there won't be a dot product between them. You'll just get 0. The last way we can combine vectors is the cross or vector product. Here we get the largest answer if two vectors are perpendicular instead of parallel. We can write the cross product as A cross B is magnitude of A times magnitude of B times sine of theta. The vector product has to be a three-dimensional idea since G is going to be perpendicular to both A and B. If you want to see how to do this with the component method, if you've had linear algebra, it's pretty easy. If not, it might look crazy. And you would not be expected to know this formula. I would give it to you if you needed to know it. But what you get out of this, again, only familiar if you've seen that, the way you find gx is to multiply ay times bz and then subtract az times by. Same thing happens in a cycle with gy and gz. We don't really have a use for it until we get to torque. That's the cross product of R and F. If you're trying to change a tire and you want to loosen the lug nuts, although here this shows someone trying to tighten the lug nuts, your ability relies on three things. It depends on how strong you are, which is the length of this green arrow, the force, the length of the tire iron, which is the red thing, and then your ability to apply force perpendicular to the tire iron. So if you look at the left picture, this is going to be hard because the force is large, but the tire iron is very, very short. The angle is perfect, though, so you got that going for you. The middle picture, you've got a long tire iron, small force, good angle. And in the right-hand picture, the force is large, the tire iron is large, but you've got a better, larger than 90-degree angle here, so you don't get as much out of it. Part of your effort is basically spent trying to snap the lug nuts off. But we'll see this when we look at cross products in relation to torque, and that'll be a little while.